Now, we mentioned in the last video that we wanted to have a nice mix between the hardwired control unit and the micro-coded control unit. So I've gone ahead and I've reintroduced the choice of the registers for the set and enable using the hardwired version. So you'll notice if you look back at previous designs for the control unit, we did have in the Reg B enabled and the Reg A enabled, and those came from the 4 least significant bits of the instruction. Now what I've done here is I've just added in the tunnels for these. Okay, so these will just point to instruction register 0, instruction register 1, and then 2 and 3. So that's just the contacts down here. And we've also got the register set for the Reg B done that same way. Now what we do is we also take out the extra bit here which feeds into our ROM and this micro-coded ROM unit, and this extra bit here will tell us whether we actually do set Reg B. And there's another 2 bits here which come out of the micro-coded control unit which tell us whether we actually are going to enable Reg A or enable Reg B, and that's these 2 lines you see here. So other than these 3 lines going back into the micro-coded control unit, the set and enable for the Reg A and B is just the same as it was previously. So now it means that the Reg A and B set and enables are still just determined by the hard wiring given by the 4 least significant bits of the instruction. But the rest of the design, that is the flags, temp, control, instruction, register, and so on and so forth, that I've numbered here, you can see them 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and there's 16, 17, 18, 19. These are all wired into the micro-coded controller here. Now, I've also had to go ahead and change the actual code here, but the point about doing this is that we cut down on the complexity of this ROM. So the ROM previous to me doing this had something like 688 lines out of 1024. So by creating the part hardwired, we've now gone down to a ROM which is a lot smaller. It's only 64 bits, and of those 64 bits we're only using 56 of them. So we've got 56 lines here in this ROM that will control all of our instructions. So that's a lot neater, a lot tidier, and a lot simpler. Of course, we lose out a bit because the complexity increases of the wiring. But again, we want to just get that happy balance. So let's go ahead and I'll quickly show you the spreadsheet that I used to generate the control values for the ROM. So this is the spreadsheet here, and it's just similar to the previous spreadsheet, but we've got rid of a lot of the columns. So we've got rid of the R0, 1, 2 and 3 set and the enables, and they've been replaced just by a single column here that does your Reg A enable, and a single column here that does your Reg B enable, and there's a single column over here that does the register set Okay, so this is reg B set, this one here. So this means that we've cut down on the complexity. So previous to this we had 64 lines for the add command. Now we've only got 4. So it simplifies things a great deal. Now, in order to generate this, all you have to do is you note that you've got the most significant bit here, which is 4 bits, and the 2 least significant bits, which are going to give you the position. In fact, I never mentioned that in the diagram, so once we finish this, we'll go back to Logisim, and there's another section there which I never talked about, but we'll go through this first of all. So we're going to have the position defined by these 6 bits. Okay, so 2 to the 6 is 64, so we're going to have 64 possible options here, and you can see that we only actually use 50. There's less than 55, there's 3 less than that, so we only use 52 of them. Okay, so we've got a few left over, spare. And the steps here are steps again for the stepper, 4, 5, 6 and then stop for each of these ALU instructions. And for other instructions there we've only got maybe 4 and 5. In fact, for the jump register instruction we've only got position 4 gets used in the stepper. And for each of these we just have to put in the value for the 0 or 1s for each of the outputs of the control unit. Now after I did that, I've got this generate hex, so when I click on that it just goes over to the very end and it takes everything that we have along this row here and it generates the hex number. So we've got a 20-bit number here and it just generates the hex value for it. And then the other one here, binary to decimal, it takes the address here. So this is the address that you see here, the 100000, and it generates the binary for that. It generates the decimal for that binary number, and it just gives us in effect, it gives us the position within the ROM. But of course, whenever we put this in, we're going to have a few spare places. So we're going to have 64 bits in the ROM, but we have to position them in the right position. Okay, so we've got 50, something like 52 are getting used and the other 12 are spare. But every bit has to sit in the right position. So what we have to do is we've got to put this into order. So again, I just generate the order here, reorder hex, and that's it, going in and just regenerated the orders here. So it means that the 0th bit position will contain this. So this is the output for the ROM. And that's all of the outputs there for the ROM. And finally, you can go ahead and you can export it. Okay, so you can export it as usual. Now, once you've exported it, you can open up the file, and I'll show you the file in here. So it's just called microcode. So this is the microcode file here. Okay, and then we load that into the design. If I open up this design here, so that's the ROM there. So you go in there and we can go edit contents, open, and then you open up the file here, and it actually gives you the option. So it's a version 3 hex. We have to click on that there, and it'll load in the values. Okay, so that's it, loaded all the values in. Now if we were to run through an example, so we could pick again the simple example. So it's all reset. So I'll go in and we've got the ROM's got the jump to the position in the RAM. The RAM we could put in the data command and we'll load in 0f and we'll end it. Now again, I've got a different value for the end because we've changed the code about a bit. So the value for the end in this one is 70. But don't worry too much about these changes because the control unit is in flux at the moment. We'll continually update and add sections, and as we update and add sections, little things will have to change. Okay, so that's the program there. User panel, and we can actually step through. So if I was to step through this, you see it. Instruction registers 40, which is the jump, and it's telling it to jump to the first address in the RAM. Now the first address in the RAM is this address here, so it's going to jump to that address. Now when it's jumped to that address, it pulls out the instruction from that address, which in this case is the data instruction. So the data instruction adds the value 0f into the register R0, and then it just continues on and it ends there. Okay, so that is how this is working for the moment. Now there's another little thing here that we can note, and it is that in the next video what we want to be able to do is we want to be able to have an option to write in complex instructions. So we want an option to count up to our 16. So we're going to replace this little section here, and I have decided exactly how I'm going to do it, but it appears to me what we want to do is we want to keep the stepper counting 1, 2, 3, because these 1, 2, 3 are for the fetch and these are hardwired. But the rest of the options here from 4 up to 16, in effect, they only really perform one function, and that function is to increment the ROM. So the instruction comes in here, it finds the beginning of the beginning of the instruction in the ROM, and then the counter will then increment that, and it'll increment it just by a value of 1, and then another one, and another, and it'll keep doing that up to a maximum of 16. But what it'll do is whenever it gets to the end one, so it might get to 4, 5, 6, but at 6 we'll put in a stop, and that stop will come back, and again it'll jump back to the next fetch. So we can do that in the next video. One other thing to note here is that the instruction now, the bottom 4 bits are hardwired, so we don't need those 4 bits in order to find the correct address in the ROM. All we need is the top 4 bits. Okay, it's because it's the top 4 bits that are going to hold the actual instruction, and it's the instruction we want to decode. We don't need to decode the sets and enables for the register A and register B, because we've just put those back in as hardwired elements. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.